Good morning, welcome to new lecture. Today I will solve again several examples. If you remember, we had this problem last session. We had one rigid beam. Here we have hinge, one rod here, another rod here, point O, B, C. This angle theta, it is 30 degrees. From here to here it is L, and this is L2, and this is rigid beam. If we apply external load at point O in vertical direction, this is external load, magnitude of external load, it is P by applying vertical direction. Problem statement asks, determine the ratio of internal force FOB over FOC. What is this ratio? Let's look at the problem nature. If we pull down point O, because this beam is rigid, for example point A, this rigid beam will rotate respect to A, and here we will have downward deformation like delta. If we have deformation delta over there, and Young modulus is E, cross-sectional area is A, Young modulus it is E, cross-sectional area it is A. The stiffness for OB will be equal to EA over L. The stiffness for member OC in vertical direction will be equal to EA divided by length of OC. Length of OC we don't know, but we know length of OB. Length of OB is equal to length of OC cosine 30 degree. So from here we have length of OC is equal to, because OB it is L, it will be L over cosine 30. So here I should put L cosine 30 times cosine squared theta cosine squared 30. This will be stiffness of this OC member in vertical, in deformation direction. Internal force in member OB will be stiffness of that member EA over L times deformation. Internal force in OC now we cannot find, but we can find internal force OC component in vertical direction, because we have stiffness in vertical direction. So internal force OC component in vertical direction will be equal to, this is stiffness, which is EA over L cosine cubic 30 times delta. So this cosine 30 multiplied to cosine 30 will be cosine to the power of 3, cubic cosine. So now we know here, if this is OC, the component of OC, the component of OC in vertical direction is here, and this angle is 30 degree. So we know OC in vertical is equal to OC times cosine again 30. From here FOC will be vertical component divided by cosine 30. Again, if I divide this by cosine 30, will be EA over L cosine square 30 times delta. We have FOB, we have FOC. The ratio will be FOB divided by FOC is equal to EA over L delta divided by EAL cosine square 30 delta. Delta and delta, they will cancel. EA over L, EA over L. So the answer will be 2 over square root of 3. From here, 2 over square root of 3 squared. This will be equal to 4 over 3. So this ratio, we found this ratio. The ratio of OB over OC will be 4 over 3. It means contribution of the OB will be greater, will be more than OC, or OB member will observe more force, and force, internal force, will be greater than OC. Let's look at another problem. We have one rigid beam. This is A, B, C. This beam is rigid. L, E, A. And this is L, E, A. Due to manufacturing error, this member, for example, A, B, C, D, E. This member, DC, is shorter than L, a little bit. For example, if this is 1 meter, this is 1 millimeter is shorter. A little bit, it is smaller than the L. So L is supposed to be the length of DC is supposed to be equal to the L, but due to manufacturing error, a little bit it is short. And what is this gap? That gap, it is delta naught, and we know that it is known value. For example, if this length is 1 meter, this is 1 millimeter. We apply force here, we apply tension, and we bring this point down and we attach to point C. So if we apply load for this member DC, which is shorter delta naught, and pull that, we will have elongation, so it will reach to point C. We attach that. After attaching, we release that. So what will happen? We will have tension force here, and again we will have tension force in this member too. So member DC, internal force will be tension force. Member BE, again internal force, we have tension inside of the DE. What is that force? Magnitude of that force. So internal force DC is unknown. We want to find that. And assume from here to here it is L again, this is L2. So if I pull down this member DC and then I attach to point C and release it. What will happen? We will have elongation in this member, and this member C again will go up. So a little bit we will have elongation in member DC, and a little bit point C will go up. It will reach to each other and we connect to each other. So if I assume, let's say show a little bit here, there I think it will be difficult to show, or maybe with other color I can show it. Let's. If this point go up a little bit, delta, this will rotate a little bit. Of course it will remain a straight line, but it will go a little bit up. If this deformation is delta, if point B go up delta, point C will go up how much? 2 delta. So if point B goes up delta, point C will go up to delta. Why? Because initially this is member ABC, it is rigid beam. Then this is point A, point B, point C, A, B, C. Then point B, we assume delta will go up. Point C should go up to delta because this is triangle and this length should be proportional. So if I assume this is y, delta over y should be equal to L divided by 2L. From there we can find y is equal to 2 delta. So if this point B go up delta, point C will go up 2 delta. So what is the remaining gap? Remaining gap here, if this is delta naught, what is elongation in this member? It will be delta naught minus 2 delta, because this is delta, this is 2 delta. Entire this distance it is delta naught. So elongation in this member will be delta naught minus 2 delta. So if we have this situation, look at to the beam again, A, B, C. Deformation here is delta, it goes up. Tension force here will be the stiffness of this member, which is EA over L times delta. If this goes up delta, this point will go up 2 delta. But elongation in this member will be delta, not elongation will be delta, not minus 2 delta. So elongation in that member will be delta, not minus 2 delta. Internal force in this member will be stiffness of that member, EA over L times deformation of this member, which is delta naught minus 2 delta. So this is force BE, this is force DC. Now if I take moment respect to point A, what I have? F DC times distance from here to here, 2L, minus F BE times from here to here, L should be equal to 0. From here, F DC, 2 times of F DC will be equal to F BE. So if I plug from here the values, what I will end up? I will end up with EA over L. If I show with K stiffness, it will be easier to write like that. It will be K times delta naught minus 2 delta is equal to, let's see, everything is right. So, FDC times 2L minus FB times L is equal to 0. That part is right. If I take to other side, L and L, they will cancel each other. 2FDC will be equal to FBE. That is right. So, K times delta naught minus 2 delta times 2, because this is FDC, times FDC, I brought from here, times 2 will be equal to FBE. FBE, again, this is K delta. K and K, it will cancel, so 2 delta naught minus 4 delta will be equal to delta. From here, if I take to other side, it will be 2 delta naught is equal to 5 delta. Finally, delta will be equal to 2 delta naught over 5. Delta initially was unknown, but delta naught, it is known value. Now delta is known value too. Because we have delta naught magnitude, we will plug here, we will find delta. If we find delta, problem statement asks internal force in member DC. Internal force in member DC is equal to stiffness of that member, EA over L times delta naught minus 2 delta. If I plug delta from here to here, it will be EA over L times delta naught minus 2 times 2 delta naught over 5. So let's I write like this. It will be delta naught minus 4 delta naught over 5. This will be EA delta naught over 5L. Because E Young modulus for material, rod material, is known value. A cross-sectional area for that rod or cable, it is known value, we can measure it. Delta naught, it is initial manufacturing error. We know how much it is short, so delta naught, it is known value. L is length for this member. Again, that is known value. If I plug here, we will find internal force in this member due to initial manufacturing error. So we will find that. I give you one problem. Try to solve yourself. I will not solve it, but I will explain the problem statement here. It is very similar to this, and try to solve yourself. We have 3 rods, and you see rods both ends are hinged, or I can draw better like hinge support like this. This is horizontal rigid beam, and it is level, it is horizontal direction. This is again L. L. From here to here it is L. This length is L. Young modulus for this member it is E. Cross-sectional area it is 2A. Young modulus for this member it is E. Cross-sectional area it is A. We have another member here. Cross-sectional young modulus it is E. Cross-sectional area it is A. This is 2A, A. Young modulus is E for all three members. And you see length 2L, 2LL, and this is L and L. This is point A, B, C. Member 1, member 2, member 3. This member 1, again, due to manufacturing error, it is short. How much it is short? Again, I show with delta naught. It is known value. For example, if this is 2 meter, this is 2 millimeter or 1 millimeter. Again, we pull down this, we pull up the point C, we attach together, and then we will release this system. What will be internal force in member 1? So you know, E is known, A is known, delta naught is known, L is known. Your final answer should be in terms of EA over L times delta naught. But coefficient, you should find that. So what will be F1? Try to think about this and try to solve yourself. Thank you so much for watching this lecture. See you next session. Bye bye.